Yay, another monitor video. Everybody loves monitor videos. Anyway, here are our hypertrochoid patterns in the centrifugal and centripetal magnetism as exists on either pole. It doesn't matter whether it's a square magnet or a ring magnet or a cube magnet or a cylinder magnet. Now these hypertrochoid patterns are interesting, but we're not interested in pretty pictures, as pretty as they are. I give you is a formula for determining the parameters of the centripetal field and the centrifugal field, and of the divergent and convergent boundaries of a perfect magnet. As we all know, or at least most of us know, a magnet has a lot of variables. I mean, it depends on how it is centered, it depends on its Gauss rating, it depends on this geometry. Too long of a magnet, if it's not Gauss right, it's not pulsed right in its creation. There are a lot of variables in the magnet. So this is the field. It's still a useful formula, but it's the first of its kind for determining where your field parameters are on a magnet simply by using the golden ratio, the golden section. Here we have our magnet outlined in white, and all we have to do is determine our C3 radius and multiply that times 5 to the power of negative 3, which is 0.23606, which is our C4 radius, which is our centripetal boundary. You take your C3 radius, the magnet, multiply that times 5 to the power of negative 2, 0.381966, and you end up with your C1 radius. And you'll draw this out here in a second. And your C1 radius of your centripetal, which also draws out the boundary of the dielectric boundary, also draws out the boundary of the magnet. You multiply your C1 radius times whatever that is, times 3.23606. All of this is an absolutely incommensurate system. This is the golden angle. You can look up, do a Google search on 137.5077 degrees. And 1 is also the golden angle of 85 degrees. So you have your incommensurate circles of divergent centrifugal magnetism, the magnet itself, whatever that is. You can take any size of the magnet. You're able to extrapolate from that using my formula that I came up with. Now, this is under a perfect condition, perfect magnet, perfect geometry. Obviously, there are so many variables that this is not applicable in most cases, but if you have a perfect magnet, this is still applicable in understanding what the field parameters and geometry of the magnetic field, both centripetal and centrifugal, are. And you have your centripetal radius here, which is 5 to the power of negative 2, and you have your both. The gyromagnetic precession, what turns out to be extremely interesting in this is that your centripetal point on your magnet, remember the white circle is the physical magnet looking down on either pole. This inner small ring, which is 5 to the power of negative 3, which is 0.23606, also is the point of the centripetal boundary. But it is, importantly, the gyromagnetic precessional angle of the inner atomic. So the gyromagnetic precessional angle is also the centripetal boundary. So, let's take a look at this chart again, but let's do what you should always do, and of course, put tape on your monitor, and let's take a look at how we can create our magnet. I just do this because it is hard to draw a circle using a computer mouse. So, let's start by drawing out our both magnet and our dielectric boundary, because the dielectric boundary and the magnet are one and the same. Now let's draw out our centrifugal field boundary using the formula that we have. Remember, we adjust this for whatever the parameters of the magnet are. So now we have our centrifugal field. Now let's draw out the centripetal boundary right here. It was a little too large that time, but I can do it again. So, here we have our centrifugal field, the field of magnetism. What we have here, let me draw it out for you a little bit better so you can see it. Here we have the physical boundaries of our magnet looking down on either pole. Here we have our centrifugal and centripetal interlacing in perfect golden section incommensurability as seen in ferrofluid demonstrations using the ferro lens created by Tim Venderelli. And here we have our gyromagnetic precessional angle, but this is also, remember, this is our magnet right here, our physical boundary of our magnet. Here we have our centripetal point, where you can actually measure the Gauss rating here. You notice that we have fall off here. So if you look at this in 3D as it's reciprocating to the other side and returning centripetally. So this is leaving here, but we have max velocity at our divergent edge of the physical magnet. Our centrifugal max velocity is, of course, at the boundary of the physical magnet, which is also, of course, the boundary of the dielectric of the physical magnet. So max velocity centrifugal is here, curving around. You can't see it obviously to the other side. So we have our max velocity, and so we have curvilinear field reciprocation, centrifugal and centripetal. Let's do that again really quick. Like I said, it's just so impossibly hard to draw a perfect circle using a computer mouse. I'm just using this print overlay. So here we're drawing the boundary of the dielectric and also centripetal reciprocation, because the two are synonymous. And it doesn't matter whether you draw one clockwise or the other one counterclockwise. You end up with the same hypertrochoid pattern regardless. So while magnetism reciprocates that way, it's not necessary, nor does it change the field parameters and how the ultimate resultant looks. The only way you're actually determining clockwise or counterclockwise is through the pressure conjugation, but not in the ultimate pattern. And here we have our centripetal point. And so here we have it. Once again, it's our boundary of our magnet. Here is our centrifugal divergent magnetic field. Given a perfect magnet, this formula holds, which there never is a perfect magnet or perfect geometry. But if you have a magnet with a base of phi and a height of 1, or a base of 1 and a height of phi, it's made perfectly, created perfectly. You have an ideal magnet that is created under ideal circumstances, so you have a point of variance not over plus or minus 10% given such a type of magnet. So you are still able to extrapolate what the field parameters are, where the centripetal point is. This is proven with the Gauss meter. This is proven with the field boundary. So all you have to do is use my simple formula. And also this is good for illustration tool. Like I said, this formula never existed before. So like I said, you could change these points. See, I just have one specific magnet shape drawn here, but I mean, you can extrapolate this larger or smaller depending upon the surface. It doesn't matter if it's a square magnet or not. You just take the circle of the max face of a square or a cube magnet, and you still end up with the same thing, because as I showed you in the other diagram here, you can see we have a cube magnet. It doesn't make any difference, because centripetal and centrifugal magnetism doesn't see cubes and squares and cylinders. It only sees field pressure mediation. So same thing on cube magnet. It doesn't make any difference whatsoever. So let's get this out of the way. Let's do that one more time for clarity's sake, and then we'll go back to the chart. So using my simple formula, you'll be able to determine. It's extremely useful for educational purposes. You don't need, like Eric Dollard, you don't need extremely complex. Nature doesn't do math. She only does field pressure mediations. So let's draw out our dielectric boundary and our centripetal reciprocation. If I was drawing it there, which apparently I wasn't. I'll get back on the program. Okay, let's try that again. Okay, here's our dielectric boundary, and also the physical boundaries of the magnet, and also the convergent reciprocation of centripetal magnetism. But that's not the centripetal boundary. Now let's draw the centrifugal field of the perfect magnet. So you can adjust this to the size of any magnet. It'll still be the same. It has to be. It's necessitated. The Greek ananke. Now let's draw our centripetal boundary. Here we go. And let's take a look at what we got. Yep, here we go. Here we have our physical magnet. Here we have our centripetal boundary. And here we have our centrifugal reciprocation, mutual reciprocation between centripetal and centrifugal. From one side to the next, obviously you only see one pole at one time, but you're able to extrapolate under perfect situation, even if it's quasi-perfect, you're able to get within maximum divergence of, 15% of what your field boundaries are. Meaning before the centrifugal starts terminating. Of course, you still have field lines extending further out past this, but the magnet follows the golden ratio of field reciprocation. Now, another important point, if you see this blue line we have here, right here, the point of divergence before I start drawing a circle is also the exact same diameter of the centripetal boundary, which is phi to the power of -3. Another interesting point. So before I start drawing either the dielectric boundary or the centrifugal boundary, I have to first draw out a line and a returning line. So I start the circle here and I leave the circle here. So I diverge, I diverge and I converge at a ratio of phi to the power of -3, which is 0.23606. Another interesting point. I mean, it's perfect golden section, golden ratio, incommensurable field reciprocation throughout. One last time before we go back to our charts. Here we go. Went a little too far on that one, but it's close enough. It's hard using a physical mouse. Here we have our centrifugal boundary of our magnetism existing outside of the physical magnet. And lastly, let's draw our centripetal boundary showing our magnet. And here we have it. Let's define the boundary of our magnet a little bit better. So here we have it. The green lines are our converging centripetal magnetism concentrated at right here. Now you have to think three-dimensionally. So you have this further away, so your magnet is over here. So you have your converging centripetal magnetism starting here at a boundary in space commensurable with the centrifugal and coming here. Remember, max velocity is at the apex. And just the opposite of that, our centrifugal divergent outwards, max velocity at the boundary of the dielectric plane. So that's max velocity there. You have intermediate pressures which reciprocate along to the dielectric inertial plane rather than making it all the way around to the other side of the magnet. So max velocity here, our divergent centrifugal magnetism reciprocating around to the other side. This is all golden sections. Absolutely every bit of it. This formula, first time you've ever seen it, very, very simple. So if you know your magnet radius, all you have to do is multiply that times phi to the power of -3 to get your C4 radius. You take your C3 radius and multiply that times phi to the power of -2. That gives you your dielectric boundary radius. And you take your C1 radius, whatever that is, say it's 1, or whatever it is, doesn't make any difference. You take the radius of C1, extrapolated from C3, which is your physical magnet, so you multiply that times 3.23606, which is phi plus phi, and you end up with your C2 radius of your field. So that's where your C2 radius is right here. You don't want the 3D effect like I was just using in that Doodle program, which all it does is draw perfect geometrical shapes. Remember, these angles right here are the golden angles that make up a... it took me 4 years to finalize this proof on another diagram. It took me, well, 4.5 years to prove it, but in a 360-degree circle, the division of a circle in perfect golden incommensurate sections, I did a whole lot further than this, but it's too complicated to go into here, but it's 137.5 degrees, 2 of those, which equal phi, and 1 over here, so you can actually see it over here. These 3 triangles, the 137.5 degree triangles, 2 of those, and 1 triangle which equals 1, the golden angle of 85 degrees. Those make up the 3 sections of the incommensurate circle, which also make up the centripetal and centrifugal reciprocations. This is proven physically using the ferrocell. It is proven. Now, of course, like I said, a magnet has I think 20-some variables, and of course one of its geometry, how it's centered, what its Gauss rating is, etc., etc., etc. But say you have a perfect, very well-made neodymium iron boron magnet, you'll have a max divergence of no more than 15 to 18% difference. But the important thing is that this is the model for the perfect magnet with a perfect geometry. And actually some of the magnets, if you actually buy the 3/8 by 3/8 inch magnets that are N48 or N50 Gauss, and they come within like 98 or 95% of what this model is. So you're able to extrapolate where your centrifugal field boundaries are for field reciprocation. Just using this simplex formula. C3 radius times 5 to the power of -3, C3 radius times 5 to the power of -2 for your C1 radius, which draws out your dielectric boundary. And just to extrapolate from your C1 radius, all you have to do is multiply that times 5 plus 5, which is 3.23606. So whatever your C1 radius is here, you multiply that times 3.23606, and you end up with your C2 radius. But first you have to draw your 3 incommensurate triangles. Both of these are phi with a apex angle of 137.5077 degrees, and your other angle, which equals 1, the golden angle here, which is 85 degrees. So you have 137, 137, and 85. Technically 137.5077. And as you can see over here, all our our entire magnet operates off of the golden section. So you have your centrifugal is equal to phi. The magnet is 1, which is phi minus phi to the power of -1. You have your centripetal. You have your centripetal, which is phi to the power of -2, and you have your gyromagnetic precession and your centripetal boundary, which is phi to the power of -3. So you have phi, 1, phi to the power of -2, and phi to the power of -3. Everything within a perfect magnet. Like I said, there is no perfect magnet. There's some that most come, your perfect, very well made neodymium iron borons come extremely close. So, like I said, there's so many variables involved. The formula for any and all magnets is absolutely impossible, logically and necessitatively so. But this is an extremely simple formula that a 10-year-old could use to extrapolate your field parameters of a magnet. So, you saw it here first. This is my discovery. This is the first time you've ever seen this in the world. Made things really, really simple. Just simple. And, you know, this is what a magnet is. I said magnetism and dielectricity don't care if it's a square magnet like this. You get the same hypertrochoid pattern. Doesn't make any difference. This is a ring magnet. Same thing. And all that is expanding centrifugal spheres or shrinking centripetal convergent spheres. So nature just takes straight lines and she bends them. I mean, that's all the 4 field modalities are. Is the ether is the ether is the ether, as I've said in other videos. So all you have to do is just take straight lines and bend them the way nature wants to make up your 4 field modalities of electricity, dielectricity, magnetism. Remember, magnetism is radiation. Polarization equals radiation equals divergence equals the creation of space. So here we have the boundary of our magnet, which is also the boundary of the dielectric. Here we have the boundary of the centripetal. And of course, all of this dielectric boundary is the boundary of reciprocating and interlacing. You obviously have your centrifugal and centripetal fields interlacing between each other against lowest pressure gradients. Obviously and necessitatively so. As the Greeks called it, anankie. Or as Russians would say, absolutno savsyemto. Spent 4 years living in Russia. That was anyway. This is our centrifugal field of divergence reciprocating around to the other side. You're only looking at one pole here, so you have your physical magnet, you have your dielectric boundary, you have your centripetal point. You can measure these points: centrifugal Gauss rating, centrifugal Gauss rating all around, and the high centripetal Gauss rating right here. Simple Gauss meter will tell you that. And here you have, with a perfect magnet, your divergent centrifugal field. As Faraday called it, the field of dielectricity, quote unquote. Anyway, you saw it here first. I'll post up this chart online underneath the video so you could download it so you can see a nice crisp, clear copy. This should be, at the very least, extremely good for educational purposes and shows that Mother Nature, with the dielectric and the magnetic, the interatomic magnetodielectric, which makes up the magnet, due to a disequilibrium of the interatomic and the creation of a permanent magnet, this is how nature mediates her fields. They're all golden section, golden ratio. Phi, 1 over phi. All phi cubed, 1 over phi to the power of negative 3, which is phi cubed, which is 4.23606. And guess where I discovered that 10 years ago? It's a text that originally belonged to Pythagoras and was handed down to Plato, and it's in Plato's Republic 509d to 511. I found and discovered that secret 10 years ago, and look where it eventually led me. First I found the proof, and then I found out that, well, look at this. This is exactly what I discovered 10 years ago. Mother Nature mediates all her pressures along golden section and golden ratios under ideal perfect conditions, which obviously are almost non-existent, but given the perfect condition, this is how she mediates her pressures, just field upon fields mediating themselves against lowest pressure gradients. You saw it here first, and now you've got the formula located up here. Like I said, you can download the chart. It'll be a link at the bottom, and thanks for watching.